Welcome to the GeoMethod channel. Today we are solving another interesting geometry problem. Here is today's challenge. Can you find R? 3 ways through perpendicular chords. Take a moment to study the figure. Then let us explore the 3 methods and the geometric ideas that connect them. A vertical chord AB is cut at P into lengths 4 and 44. From P, the 8-unit segment PC reaches the circle at a right angle to the chord. Find the circle's radius. The diagram carries only these givens. The radius is not written on the graph. Read the blue chord first. P splits segment AB into the short piece segment AP equals 4 and the long piece segment PB equals 44. The compact labels sit beside the exact segments they measure. Together, the two pieces make the full chord. Segment AB equals 4 plus 44, or 48. The pink segment CP has length 8 and meets segment AB at a right angle at P. Point C lies on the same circle. Method 1 uses coordinates only as a measuring frame. Put P at the origin, keep the displayed chord AB vertical as the y-axis, and let the perpendicular segment PC point along the x-axis. Nothing in the geometry is rotated or changed. Since A is 4 units above P and B is 44 units below P, write A as 0, minus 4 and B as 0, 44. Point P is the origin, exactly where the two perpendicular directions meet. Because segment PC is 8 units straight to the right, C is 8, 0. First insight. The center lies on the perpendicular bisector of every chord. The midpoint M of the 48-unit chord is 20 units below P, so the center must lie on the horizontal line through M. Its y-coordinate is locked at 20 before we solve anything else. Only the horizontal offset remains unknown, so write the center as x, 20. This single unknown x tells us how far the center sits left or right of the chord. Both A and C lie on the circle, so segment OA and segment OC are equal radii. That equality will remove the unknown radius while we locate the center. In the right triangle, from O to A, the horizontal leg is x, and the vertical leg is 24. Pythagoras gives segment OA squared equals x squared plus 24 squared. For radius OC, the horizontal difference is x minus 8, and the vertical difference is 20. A second use of Pythagoras gives segment OC squared equals x minus 8 squared plus 20 squared. Second insight. Equal radii mean these two squared expressions are equal. When we compare them, the x squared terms cancel, leaving a linear equation. Solving it places the center 7 units to the left of the chord. X equals minus 7. The remaining linear equation gives x equals minus 7. The negative sign simply means the center is 7 units to the left of segment AB. So O is minus 7, 20. 7 units left of P and 20 units below it. Now look at radius OA. Its two perpendicular legs are 7 and 24, so Pythagoras gives r squared equals 7 squared plus 24 squared, which is 625. Therefore, method 1 gives r equals 25. The coordinates only organize the two perpendicular directions and their distances. The circle, chord midpoints, equal radii, and right triangles are geometric facts. The geometry itself does not depend on the axes. Now let us remove the coordinates and solve the same problem directly. Here is the second method. Set the coordinate equations aside and return to the original givens. Extend segment CP through P until it meets the circle again at C'. Now, segment AB and segment CC' are two perpendicular chords crossing at P. Power of a point at P pairs the two pieces of one chord with the two pieces of the other. Watch segment AP and segment PB flash together first. Then watch segment CP and segment PC' flash together. Their products must be equal. Segment AP times segment PB equals segment CP times segment PC'. Substitute the three known lengths. 4 times 44 equals 8 times segment PC'. Divide by 8. The missing chord piece segment PC' is 22. Without coordinates, the same midpoint is easy to read. Along chord AB, the imbalance between 44 and 4 is 40. Half of that is 20. So M lies 20 units from P toward B, and the center lies on the perpendicular through M. Apply the center chord theorem again to segment CC'. Its pieces are 8 and 22, so their midpoint N lies 7 units from P toward C'. The perpendicular through N must also pass through the center. The two perpendicular bisectors meet at the center O. Relative to P, the center is 7 units toward C' and 20 units toward B. From A to O, the legs are therefore 7 and 24. Now, Pythagoras on the right triangle from O to A gives r squared equals 7 squared plus 24 squared. That is 625, so r is 25 again. The second method is independent of the coordinate equations. Power of a point completes the missing chord, and the two chord midpoints locate the center. It confirms r equals 25. Method 3 is the fastest. The perpendicular chord's diameter theorem says that the squares of the four chord pieces add to the square of the diameter. Since the diameter is 2r, we have 4r squared equals segment AP squared plus segment PB squared plus segment CP squared plus segment PC' squared. Here is the next insight. The four squares give r immediately. Substitute segment AP equals 4, segment PB equals 44, segment CP equals 8, and segment PC' equals 22. Their squares add to 2,500. Thus, 4r squared is 2,500, r squared is 625, and r is 25 in one line. Why does that identity work? The chord midpoints form a right triangle from P to the center. Doubling its legs gives the whole length segment AP plus segment PB in one direction, and the imbalanced segment PC' minus segment CP in the other. Pythagoras gives the displayed equation. When it is expanded, power of a point makes the two cross terms equal and opposite, so only the four squares remain. Three methods now agree. Coordinates expose the center, power of a point completes the missing chord and lets the midpoints locate the center, and the perpendicular chord's identity compresses everything into one line. The center chord theorem was used 3 times, once in the coordinate method, then once for each chord in the direct geometry method. Its quick contribution is simple. The two chord midpoints draw two perpendicular bisectors, and their intersection is the center O. Pythagoras was applied 4 times across the two full methods. The memorable final use is the 7, 24, 25 triangle. 7 squared plus 24 squared equals 25 squared. Power of a point was used once. Watch segment AP with segment PB flash first, then segment CP with segment PC'. Their equal products turn the unknown fourth chord piece into 22. The perpendicular chord's diameter theorem was used once, and it is the fastest finish. The 4 squared pieces add to the diameter squared, so 4r squared is 2500 and r is 25. Therefore, the circle's radius is 25. The strongest lesson is not only the number, but how the same geometry can be read through coordinates, chord products, or one compact perpendicular chords theorem. So the final answer is 25. A good geometry problem often has more than one beautiful solution. If you see a genuinely different construction, a high-level idea that leads to another solution, or a thoughtful adaptation of an existing method, share it in the comments. Even a rough idea is welcome. A sketch of the key move is enough. We greatly appreciate these contributions. With your permission, we may feature the approach in a future Viewer Solutions episode and acknowledge you by name or channel handle. Thanks for exploring geometry with GeoMethod.